Everybody, in this video, I'm going to be going over the review sheet for test number 5. So question number 1 says, which statement is true about every parallelogram? So it is not choice number 1 because all 4 sides are only congruent if we're talking about a rhombus or a square. The interior angles are not all congruent in just a regular parallelogram. That's only true if we're talking about a rectangle, which has 4 congruent 90-degree angles, or a square. 2 pairs of opposite sides are congruent. That is true about the parallelogram, so I'm going to circle it. What that means is that one pair of opposite sides are congruent, and the other pair is also congruent, meaning that both pairs of opposite sides are congruent, which is definitely a property of parallelograms and every parallelogram-based quadrilateral. The diagonals are perpendicular to each other. I'm going to cross that one out because that's not a property of a parallelogram. That's a property of a rhombus as well as a square. In question number 2, we're told that we have a quadrilateral math, and it's a rhombus, and it has diagonals AH and MT. So in order to answer this question, since I know this rhombus has diagonals drawn into it, it's probably going to be helpful to us to think about some properties of the diagonals of rhombuses. So I know that one property of the diagonals of a rhombus is that the diagonals are perpendicular to each other. And what that means is when they intersect, they form 90-degree right angles at each of those intersection points. So they form 4 90-degree right angles right there where they meet. So the question tells us that angle HAM right over here is 12 degrees, and they're asking us to find the measurement of angle AMT, which is this angle right over here. So in order to figure out what that angle is, let me just take a second and just highlight this triangle over here. So in this triangle, I know that we have a 12-degree angle. We have a 90-degree angle because the diagonals are perpendicular. And all that we have to do is find the last angle of this triangle. And that last angle of the triangle is angle AMT. So I'm going to add up 90 and 12. That gives me 102. And if I do 180 minus 102, I get 78. So once again, in this triangle, I know 2 angles, the 90-degree angle and the 12-degree angle. When I add those up, I get 102 degrees. Since all 3 angles of a triangle add to 180, 180 minus 102 gives me 78 degrees, which is the measurement of the missing angle over here, angle AMT. In parallelogram RSTU, so the first thing I'm going to do is I'm going to draw parallelogram RSTU because the question is talking about this parallelogram, but I don't see it here. RSTU. So the measure of angle R is 5x minus 2, and the measure of angle S is 3x. What am I saying there? 3x plus 10. What we need to do is determine and state the value of x. In order to do this, I'm going to use the fact that in a parallelogram, consecutive angles are supplementary. These 2 angles, R and S, are consecutive angles because they are right next to each other. They come one right after the other in the parallelogram. Anytime we have 2 consecutive angles in a parallelogram, we know that they add up to 180 degrees. So I'm making an equation that says if I add the 2 angles together, I get 180 degrees. Combining my like terms, I have 8x plus 8 is equal to 180. If I subtract 8 on both sides, I have 8x equals 172. And then if I divide by 8 on both sides, I get x is equal to 21.5. So 21.5 is the x value here, and that's what we needed to find. If you needed to find either angle R or angle S, you would take your x value and substitute it in to find the angle measurement. This question just asked us to find x. In the next question, we once again know that we have a rhombus, and we know that angle C is 100 degrees, and we need to find the measurement of angle DBC. So let me fill in anything that I do know. So I know that in a rhombus, opposite angles are congruent to each other. So I know if this is 100, I know this one is 100 as well. I don't know if that will help me, but it's just something I can fill in to get me closer to my goal. I also know that in any parallelogram-based quadrilateral, that consecutive angles are supplementary. So I know that this angle and the one right next to it together should make 180 degrees. So if this angle, angle C, is 100 degrees, then the whole angle B should be 80 degrees to make 180, since consecutive angles are supplementary in a parallelogram. Now, I also see that there is a diagonal BD drawn into this rhombus, and I know a property of rhombuses is that the diagonals bisect the angles. So if the whole angle B is 80 degrees and the diagonal is bisecting the angle or cutting it equally in half, I know that each half of this angle should be 40. So I just figured out that the measurement of angle DBC should be 40 degrees. Number 5, we have a rectangle. So let me underline that, rectangle ABCD. We know that the measurement of angle BAC, so this angle here, is 3x plus 4. And we know that the measurement of angle ACD, this angle right over here, is x plus 28. So I know that a property of a rectangle, since it does have all the properties of parallelograms, is that opposite sides are parallel to each other. So this pair of opposite sides is parallel, and this pair of opposite sides is parallel as well. So if I highlight these two parallel lines over here and transversal AC, you can see that there's a sideways kind of backwards letter Z. And we've talked about many times in class how when we have this letter Z, in the corners of the Z are alternate interior angles. Alternate interior angles are congruent. Oh no, where did that go? Are congruent when lines are parallel to each other. So I can set up the following equation. I can say that x plus 28, this alternate interior angle here, is equal to 3x plus 4, this alternate interior angle over here. So let me subtract x from both sides and also subtract 4 from both sides, and I get 2x is equal to 24. If I divide by 2 on both sides, I find that x is equal to 12. So I can substitute back in and find what the measurement of these alternate interior angles are. My x value is 12. 12 times 3 is 36. Plus 4 is 40. So I'm going to put here 40 degrees. Now, what I need to find is I need to find the measurement of angle CAD. CAD, that's this angle right over here. Well, I know that all the angles in a rectangle are right angles. So I know that the whole angle A is 90 degrees. If this part of the angle is 40 degrees, then the other part has no choice but to be 50 degrees to make both parts of the angle add up to the full 90-degree right angle. So we see that the measure of angle CAD is 50 degrees. Okay, number 6. So number 6 probably should not have really made its way onto the review sheet because right now at this moment we don't have the tools to actually complete it unless we kind of use the answer choices and plug in to kind of figure out what the correct answer choice is. So let me draw a picture of a square and I will walk you through it on the video. But if it doesn't really make full sense, don't worry, because a question like this is not going to show up on your test. And in a couple of weeks, we will have more tools that will help you better answer questions of this sort. So I know that in this square, we have a diagonal that is length 3 radical 2. And we know that we have a square, so we know that all the angles are right angles. So I know that I do have right triangles here. And when we have right triangles, we know that the Pythagorean theorem does work. So basically what I did is I first was trying to figure out, using the Pythagorean theorem, what each of the side measurements should be of this square. Because if I know what the side measurements should be, I can add them all up to find the perimeter of the square, since perimeter just means add all the sides together. So the sides ends up being 3, and let me plug into the Pythagorean theorem to show you how and why this works out. So the Pythagorean theorem is a squared plus b squared equals to c squared, and we know that specifically for right triangles. If I test out 3 and equals to c squared. So let me try that again. 3 squared plus 3 squared equals to c squared. 3 squared is 9, plus 9 is equal to c squared. I'm going to make an arrow here to indicate I'm going over here. So that's 18 is equal to c squared. If I take the square root of both sides, I get c is equal to radical 18. Radical 18, we can break down into radical 9 and radical 2. 9 times 2 is 18. Radical 9 is just 3. And the radical 2 doesn't simplify any further. So I see here that if the side length of my square is 3, and using the Pythagorean theorem, it does check out that my diagonal, which would be the hypotenuse of the right triangle here, would be 3 radical 2, which it's supposed to be according to this question. So now I know the side lengths are for sure 3. If I add them all together, 3 plus 3 plus 3 plus 3, that would give me 12. Okay, let me move it along to the next question. So in question number 7, we're told that we have an isosceles trapezoid, Q-R-S-T. So I know, since I have an isosceles trapezoid, that the base angles are congruent to each other. So if angle Q, this bottom base angle over here, is 5x plus 3, and angle R, this other bottom base angle over here, is 7x minus 15. And I know that those two base angles should be congruent or equal to each other. So I can make an equation that says angle Q, which is 5x plus 3, should be equal to angle R, which is 7x minus 15. If I use my inverse operations, let me start off by subtracting 3 from both sides. And I will also subtract 5 from both sides as well. I get 3 is equal to 2x minus 15. Adding 15 to both sides, I get 18 is equal to 2x. And then dividing by 2 on both sides, I get x is equal to 9. The question doesn't ask for the x value. It asks for the measurement of angle Q. So I took my x value and I plugged it back in for angle Q. 5 times 9 plus 3. So that is 48. So that's answer choice number 2. 9 times 5 is 45 plus 3 is 48. Okay, here I have trapezoid LMNO and median PQ is drawn. So, keep missing where I'm at. There we go. So, oh no, why does it keep moving around like that? Okay, hopefully it stays this time. So in this trapezoid, since PQ is a median, that means it connects midpoints together. So P is a midpoint and Q is a midpoint. So that tells me that PQ is the mid-segment. I'm going to put here equally in half. Equally in half. It's connecting the midpoints of the legs. So this is the mid-segment. So if I know that LM is x plus 7, and I know that ON is 3x plus 11, and PQ, the mid-segment, is 25, it asks for the value of x. So I know from class that the mid-segment is equal to half the sum of the bases. So what I'm going to do is I'm going to add the two bases up. So that's x plus 7 plus 3x plus 11. I'm going to divide them by 2 because remember the mid-segment is half the sum of the bases. So add them up and divide them by 2. And that's equal to the mid-segment, which is 25. So in order to solve this equation, the first thing I'm going to do is, since this is division by 2, I'm going to multiply the other side by 2. So that gives me x plus 7 plus 3x plus 11 equals to 50. Okay, now I'm going to combine my like terms and solve just like a regular equation. So that's 4x plus 18 is equal to 50. Subtracting 18 on both sides, that's 4x is equal to 32. And then dividing by 4 on both sides, I get x is equal to 8. So that's the value of x here. Okay, number 9 was eliminated from the review sheet. I don't know if you guys saw in Google Classroom, but we actually don't have the tools needed in order to figure out number 9. In a few weeks, we definitely will, but for now, that's eliminated from the review sheet. Probably show up on a later test that you guys have. So here we have trapezoid trap, and we have median MQ. So median connects midpoints. So once again, we know that MQ is the mid segment. Let me write that here, mid segment of the trapezoid here, and it wants us to solve algebraically for x and y. So let's start with y. We know that when we have the midsegment of a trapezoid, the way that we find the midsegment is we add up the bases and we divide them by 2. So let me do that. Base TR is 12y plus 1. I'm going to add that to the bottom base, which is 18y plus 6. I'm going to divide that by 2, because remember, we add up the bases and divide them by 2. And that gives us the midsegment, which is 16y plus 1. So what I'm going to do first is, since the whole thing's divided by 2, I'm going to multiply 2 to the other side. So on the left side, I still have 12y plus 1 plus 18y plus 6 is equal to 16 times 2 is 32y. 1 times 2 is 2. And now I'm going to combine my like terms, and I'm going to solve like a regular equation. When I add up my like terms over here, I get 19y plus 9. Oops. Oh no. Let me backtrack that a bit. So let's combine these like terms over here. So I have 18y plus 12y, and that gives me 30. So let me write that down. 30y plus 6 is equal to 32y plus 2. Okay, now if I subtract 30y from both sides, and I also subtract 2 from both sides, I get 5 is equal to 2y. Dividing both sides by 2, I get y is equal to 5 over 2. You could also write it as a decimal, but I'm going to leave it as a fraction, as 5 over 2. Okay, now let's talk about finding x. So I know in a trapezoid that the bases are parallel to each other. So if I for a second just highlight my parallel bases and any of the transversals that intersect them, either TP or RA, I see that the upper base angle and the bottom base angle right below it are same side interior angles. And I know that same side interior angles are supplementary or add up to 180 when we have parallel lines. So I'm just going to make an equation that says this upper base angle over here, 12x minus 4, and the lower base angle below it, 7x plus 13. When we add them up, we should get 180 as our answer. So combining my like terms, I get 19x plus 9 equals to 180. Subtracting by 9 on both sides, I get 19x plus 171. And dividing by 19, I get x is equal to 9. And there we have answered the question. Okay, so over here we have a proof. So let's take a second. Let's think about what we're going to do here. And then I will show you the full written up proof after that. So before we do that, let's talk about the plan. So we know that RKMP is a parallelogram. So RKMP over here is a parallelogram. So we know a lot of things about it, because at this point we know a lot of properties of parallelograms. And we also know angle JRK, this angle right over here, is congruent to angle PMO, this angle right here. And our ultimate goal is to prove that Rjmo, so the large quadrilateral on the outside here, is also a parallelogram. So we have a couple of methods of proving that we have a parallelogram. So we kind of got to think about the information and see which method we are going to be able to prove based on the information that we're given. And I do also see that there are triangles in the diagram, this one on the left here and this one on the right. So we learned a lot about proving triangles congruent to each other. And maybe if we do that here, we'll be able to get more information that we need to actually prove that Rjmo is also a parallelogram. The first thing I want to start with is the angles that they gave us are congruent to each other. Not only do I know that these two angles, JRK and PMO, are congruent to each other, but since I know that RKMP is a parallelogram, I know that the opposite angles in a parallelogram are congruent to each other. So I know that angle R over here and angle M over here, these are two opposite angles in parallelogram RKMP. I know that they're congruent to each other. So if I take those two angles and I actually put them together through the addition postulate. So if I add the blue angle and the red angle here, I get this whole black angle, angle R. And if I add this red angle and this blue angle here, I get this whole black angle, angle M. And in the larger quadrilateral, in RJMO, these are actually a pair of opposite angles in that larger quadrilateral that we need to prove is a parallelogram. So since we already were able to figure out through the addition postulate information about angle R and angle M, that leads me to believe we might be proving that Rjmo is a parallelogram using the property that if both pairs of opposite angles are congruent, then the quadrilateral is a parallelogram. So if we were going to use that property, that would involve us getting information about angle J over here and angle O over here. I notice that angle J is an angle in this triangle here on the left, and angle O is an angle in this triangle over here on the right. So if we're able to first prove these two triangles congruent to each other, then using CP/CTC, we can get the information we need about angle J and angle O. Then we'll know that both pairs of opposite angles are congruent, making RJMO a parallelogram. So let's see how we're going to prove these two triangles congruent. I already have these two blue angles in each of the triangles. So already we have a congruent pair of angles that was from our givens. I also know that in a parallelogram, not only are opposite angles congruent, but opposite sides are congruent as well. Since RKMP is already a parallelogram, they gave that to us in the question, we know that its opposite sides, RK and PM, are also congruent. And look what we have there. Not only do we have a congruent pair of angles in the triangles, the blue angles, but now we also have a congruent pair of sides. We can get another pair of congruent angles, then we can definitely prove the two triangles congruent to each other. So let's see where that's going to come from. In RKMP, we already marked the two red angles as congruent because they were opposite angles in a parallelogram. But using that same property, I also know that angle RPM over here in green and angle RKM over here in green as well are also congruent to each other because that's another pair of opposite angles in this parallelogram, and opposite angles are congruent to each other. I also know that this green angle here and the angle right next to it, angle RKJ, are supplementary to each other. Together they make 180 degrees, they form a straight angle. And I know over here that this green angle and the angle right next to it, the one inside the triangle, angle OPM, are supplementary to each other, which means together they form a right angle. Since this angle, RKJ inside the triangle, is supplementary to this one, And since angle OPM in yellow over here, the angle inside the triangle, is supplementary to this green one, we can say that the two yellow angles are congruent to each other. Once again, the two yellow angles are both supplementary to the congruent green angles. So that means they are congruent to each other. We have a theorem that we learned about called supplements of congruent angles are congruent. So if both of the yellow angles are supplementary to congruent angles, then that also means that they are congruent to each other. And that gives us the second pair of angles in the triangles that we need to prove the triangle's congruent. I now see that the triangles are congruent by ASA, ASA. And once I know the triangles are congruent, I can definitely say that angle J over here is congruent to angle O over here by CP, These are corresponding angles in the two triangles. And now I have all the information I need to say that Rjmo is a parallelogram. It's a parallelogram because a quadrilateral that has both pairs of opposite angles congruent is a parallelogram. We proved one pair of opposite angles is congruent just now, angle J and angle O, by proving the triangle's congruent. And at the very beginning of this proof with the addition postulate, we proved that angle R and angle M, the other pair of opposite angles, are also congruent, making this a parallelogram. I just zoomed the diagram out a little bit so that you guys can see the full written out proof. So you might want to take a second and pause the video at this point and just take a look at the written up proof. It has everything that was just discussed in the plan in it. So you might want to, take a picture of it, screenshot it, and replay the video that goes through the plan part and just make sure you are clear on where all of the steps here are coming from. Okay, let's talk about this proof over here. So in this proof, we know that FGHJ is a parallelogram. So the larger quadrilateral on the outside here is a parallelogram. And we also know that FK is congruent to HL. So here's FK and here's HL. And our goal is to prove that KGLJ, so this inner quadrilateral over here, is also a parallelogram. So I'm going to keep in mind my properties of parallelograms. And the first thing that sticks out to me here is that in the larger parallelogram, as well as in the smaller quadrilateral that we need to prove is a parallelogram, is that we have diagonals drawn in. A diagonal connects vertex to vertex. So I see in the larger parallelogram, we have diagonal FH. It's connecting vertex H to vertex F to vertex H. And we do have diagonal JG. It's connecting vertex J to vertex G. And in the smaller quadrilateral that we need to prove is a parallelogram, we do have diagonal JG once again. It connects vertex J to vertex G. And we do have diagonal KL. It connects vertex point K to vertex point L over here. I might want to think about what I know about the diagonals of a parallelogram, and that might help me out here. So I know that in a parallelogram, the diagonals bisect each other. That means they cut each other equally in half. So each half of each of the diagonals in the parallelogram FGHJ are going to be congruent or equal to each other. So that means in this big parallelogram FGHJ, diagonal FH is being split into two equal parts. So one of those equal parts is FO, and the other equal part is right over here, OH. And that means that the other diagonal, what's the other diagonal? JG is also being split equally into two congruent parts. Just based on that information, if I take a look now at the inner quadrilateral KGLJ, the one that we need to prove is a parallelogram, I already see that I know that one of its diagonals, JG, is being split into two equal parts, or it's being bisected. And not only is diagonals bisecting each other a property of parallelograms, but if we can show that diagonals bisect each other, we can actually also prove that the quadrilateral that we're working with is a parallelogram. So since I already know that JG is being bisected into two equal parts, we can just show that the other diagonal, KL, is also being split into two equal parts, then we'll know for sure we have a parallelogram because we'll know that the two diagonals in the quadrilateral are bisecting each other. So there's a really easy way that we can show that because we already know that FO and HO are congruent to each other because the diagonals in the big parallelogram bisect each other. And from our givens, we already know that FK and HL are congruent to each other. So using the subtraction postulate, if we start off with FO and we subtract off FK, we're left over with KO. And if we start with HO and we subtract off HL, we'll be left over with OL over here. And that tells us that we have a parallelogram, that KGLJ is in fact a parallelogram because the diagonals bisect each other. And here I have the full written out proof. It's only 5 steps long, the way that we did it here. Of course, it's not the only way to do this proof, but this is the most direct way with the least amount of steps. And I think it is the easiest and simplest way to understand how to complete this proof. So definitely you might want to pause over here. You might want to screenshot or take a picture of the statement reason chart, and you might want to replay the plan so that you can go through each of the statements and reasons and make sure you are good with where they came from. Okay, and here we have the last 2-column proof on the review sheet. So it says here that QTVW is a rectangle. So I'm going to keep in mind my properties of rectangles. And I also know that QR is congruent to ST. And our goal is to prove that triangle SWQ, so that's this triangle over here, is congruent to triangle RVT. That's this triangle over here. So I already see where one pair of sides is going to come from. I have QR, which is part of the whole side QS of the yellow triangle. And I have TS, which is part of the whole side TR of the green triangle. So in order to take the parts of each of the sides and get information about the full sides, we're going to use the addition postulate to take our information that's too small and make it bigger to get information about the full sides. So to get the full yellow side QS, I need to take QR and add RS to it, and that will give me QS. And to get the full side TR of the green triangle, I need to take TS, add RS to it as well, and then I get the full side of the triangle TR. So if I really quickly just separately draw these triangles, because anytime you have overlapping triangles, I know these don't overlap too much, but anytime you have any sort of overlapping triangles, it might help to see things a bit more clearly if you draw them separately. So that's a Q, this is an S, and that's a W. This is an R, that's a T, and that's a V. So already through the addition postulate, we can show that QS, that's the whole yellow side here, is congruent to RT. That's that whole side of the green triangle over here. That was our goal of the addition postulate. Now we have a pair of congruent sides we can use to prove the triangle's congruent. We also know that when we have a rectangle, all of the angles are right angles. So I know this is a right angle and this is a right angle. That's this angle over here in the yellow triangle and this angle over here in the green triangle. And I also know when I have a rectangle that all of the properties of parallelograms also apply to the rectangle. I know that opposite sides are congruent, making QW congruent to TV. And if I put it into my separated triangles, we can now really clearly see how to prove the triangle's congruent. That would be side, angle, side, side, angle, side. Here's the full written up proof. So you might want to take a second and pause and screenshot or take a picture of the proof and go back and rewatch the plan and make sure you are clear where all of the steps came from. So you might want to pause right now at this moment because the video is going to keep moving. Okay, and here's the last actual question on this review sheet. So the question here is to prove that you have a rhombus, but that you do not have a square. So there's many different approaches that you could take here. So I'm just gonna really quickly go through what you could have done, but I'm not going to actually do a method because everyone can pick the formula and the method that they'd like to do. So your first thing that you have to do to prove that you have a rhombus is you first need to prove that you have a parallelogram. So remember, to prove that you have a parallelogram, in those reference packets that you got in class on the second to last page, we have all the 5 methods using coordinate geometry that you could use to prove that you have a parallelogram, and the formulas that go with them are listed as well. What you can do is you can show that opposite sides are parallel using the slope formula. You can show that opposite sides are congruent using the distance formula. You can show that one pair of opposite sides is both parallel and congruent using both the slope formula and the distance formula for only one pair of sides. That's 2 sides in total. Or you can take the diagonals, find the midpoint of the diagonals, and show that the midpoint is the same for each of the 2 diagonals. And that will tell you that the diagonals bisect each other. So the choice is yours. You just need to pick one of those methods, whichever formula you prefer, and you need to show your calculations and end with a concluding statement. So for example, if I like slope formula and I found the slope of each of the 4 sides, and I found that one pair of opposite sides had the same slope and the other pair of opposite sides also had the same slope, my concluding statement would be quadrilateral PQRS is a parallelogram because both pairs of opposite sides are parallel. So once again, your concluding statement is explaining what your calculations proved and what you are showing. So if you're showing that you have a parallelogram, your concluding statement should be explaining how you know for sure it's a parallelogram. What property of parallelograms did you prove using the formula that you used? After you show it's a parallelogram, you can definitely then show that you have a rhombus. In order to show that your parallelogram is also a rhombus, you need to prove one of the special properties of a rhombus. One property is showing that it is equilateral, that all the sides are congruent. You don't have to do distance formula 4 times for each of the sides. I mean, if you already did it for the parallelogram part, then you're all set. But let's say you use slope for the parallelogram part, and now you want to use distance formula. You don't have to do distance formula for all 4 of the sides. If you take any 2 sides that are right next to each other, any 2 consecutive sides, and you show that the length of any 2 sides next to each other are the same, that's a way to prove that you have a rhombus. Remember, if 2 consecutive sides are congruent in your parallelogram, then you have a rhombus. Or you can take the diagonals of your parallelogram and you can find the slope of each of the diagonals of the parallelogram. If they have negative reciprocal slopes, that means they're perpendicular to each other. And perpendicular diagonals are a special property of a rhombus. Those are the 2 ways that you can show your parallelogram is a rhombus. It's up to you. Either you can use distance formula with any 2 sides that are right next to each other and show they're the same. Or you can take the diagonals, find the slope of each of the diagonals, and show that they are perpendicular to each other. The final part of the question says to prove that PQRS is not a square. So if it's already a parallelogram and a rhombus, in order to be a square, it would also have to be a rectangle. So if you want to show it's not a square, then you just have to show that it's not also a rectangle. So one way you could do that is rectangles have right angles. So if you can show that there aren't any right angles, then you know it's not a square. So if you find the slopes of the sides of PQRS and none of the slopes are negative reciprocals of each other, that means there are no right angles. So you don't have a rectangle. So that's one method. Another method that you could use is you could find the length using distance formula of each of the diagonals in PQRS. If the diagonals have the same length, that would make it a rectangle. So if you use the distance formula and you show that the diagonals are not the same length, then you know that you do not have a rectangle. PQRS is not a square because it is not both a rhombus and a rectangle. You're going to show it's a rhombus, by showing parallelogram first, then a property of a rhombus. But when you try to show that it's a rectangle, it's not going to work out. Either you're going to find that there's no right angles if you're using slope of the sides, or you're going to see that the diagonals are not the same length if you're using distance formula on the diagonals. Either way, Pqrs is not going to be a square because it is not going to be both a rhombus and a rectangle. You can see the answer key, the hard copy that's posted on Google Classroom, to see this filled in over here. And then you can fill in this page, and you can also fill in the chart on the back with the properties of the quadrilaterals that we've seen in class using the hard copy of the answer key that is posted on Google Classroom.